Yes. Can
There we go.
you? Can you try to share your slides?
Do you see them?
Yes, I can see them. Okay, so our first speaker is Paolo Iengo, and he's going to tell us about ATLAS results on exotic heavy hadrons. So, well, you have 15 minutes plus 3 for discussion. I will give you a 5-minute warning. Everybody that wants to ask a question can raise his hands or her hands or make it in the chat. Okay, so you can start.
All right. So thank you very much. I will report about results from the ATLAS experiment on exotic heavy hadrons. So I would like to start with this nice plot that remind the big boost that the LHC experiments have given in the recent years in the hadron spectroscopy by finding many new structures and states. Here I'll present a few selected results on the searches with the ATLAS experiment on tetra and pentaquark in the heavy hadrons sector. So for the pentaquark study, I will describe quite in detail the recent study of the search for pentaquark in the GPSI proton state in the lambda B to GPSI proton kaon decay, looking to the experimental status, to the analysis strategy of ATLAS, and comparing the results with the LHCb ones. On the tetraquark searches, I will show an older study on the search for the X5568 resonance, again into the BS-pi pair. And then I will give some perspective of the ATLAS study on the Z plus C resonance, and then I will go to the conclusion. So in ATLAS, most of the heavy ion, heavy flavor searches are based on the selection of 2 muons in the final state with a threshold of 4 or 6 GeV. Then there is the reconstruction of the muon vertex, and normally a cut is applied to the variant mass for selecting mostly GPSI. In ATLAS, as a general purpose experiment, we do not have a separation capability between pi k and proton, and this reflects in some details of the analysis as we will see in a moment. On the bottom left plot, you see the dimuon variant mass spectrum from the run 1, from data from run 1, on which the results I will talk about are based, while on the right plot you see the same plot, so the muon variant mass spectrum with data of run 2. In run 2 we have a number of improvement with respect to run 1 because there is some improvement on the trigger which allowed to maintain the low muon threshold at a high luminosity. We have the new insertable B layer, which is a vertex detector, improving the vertex reconstruction capability, so essentially improving the resolution. And then clearly with run 2 we have increased statistics. This means that we have ATLAS has a great potential for new results in heavy flavor physics study by analyzing the run 2 data. However, let's make a step back and let's look to the study of the lambda B to GPSI proton kaon decay. As I said, this was done with the data run 1 data. The study is essentially was driven last years by LHCb, first with the first observation of a structure in the GPSI proton mass spectrum. And then later on, more recently, they have resolved this peak into 2 different states, this third states at mass of 312, and they had the hint of a fourth state in between here. There was, I mean, the Greeks experiment in photon-proton collision, psi-proton final state in the S channel did not observe any structure. However, more recently, the Dizir experiment reported the Morion conference a 3.1 sigma evidence of the PC state, but this was unresolved. So the peak solution proton channel. This is an
Paolo, we cannot hear you from time to time.
I assume Paolo is trying to reconnect. Okay, if Paolo cannot reconnect, perhaps we should go on to the next presentation.
So, okay, next presentation is by me, Antoni Szczurek. Share screen.
Okay.
So if Paolo reconnects, then we can just change the order.
Okay, perfect.
Just
Okay, we can see your slides.
it's okay.
Yes. Okay.
I
So
will start. So I will be talking about mechanism of new tetraquark production. This is a state which was observed last year by LHCb. So this is one of those exotic states which Paolo started to talk about, but didn't manage. So this is work done together with Rafał Maciuła and Wolfgang Schaefer. So this is content of my talk. So I will mention about the discovery. Then I will discuss mechanism of tetraquark production. So I will focus on mechanism of tetraquark production. I will be talking about background production. This state was observed in J-side channel. Then I will show some results for tetraquark production. Then results for the background, also results for FCC, and mention about calculation for new tetraquark 2C2B. And then I will go to conclusions. So we know that standard meson are QQ bar type. So this we know from Zweig-Gellman. Quarkonia, which we discussed extensively today, are QQ bar states with capital Q. Many years ago, Jaffe proposed that there could be such states QQ bar, which are called tetraquarks. And this was discussed in the context of MIT Beck model. Then Belle, which was mentioned, which was rediscovered now, mentioned this X state, which is, some people think it's QQ bar, CC bar tetraquark, but there is a lot of discussion about these states. But I want to concentrate on fully heavy tetraquarks, and one of them was observed in J-side channel. This is T4C 6900. So the hypothesis is that the observed state is a quantal state of CC bar system. So it's really a genuine tetraquark. So ground state of tetraquark was predicted at 5.8 Jeff, so which is much lower than the state I will be discussing. So probably, most probably, this state we observe is not ground state of tetraquarks, but one of the excited states. However, spin and parity is unknown, and different models predict that this can be either 0 plus, 1 plus, 2 plus, or 0, or even 0 minus. Of course, we don't know much about tetraquarks, so we don't know also branching fraction of the decay of this tetraquark to J-side, which my feeling is of the order of 50%, but we don't know strictly this number. So if this is really tetraquark, this genuine tetraquark we observed, so then perhaps we started new era of these new objects, and we hope that in future with high LUMI, LHC, and FCC, they could be studied. So many theoretical studies concentrated on spectroscopy, and in spectroscopy, either one does approximate approach and assume that this object consists of two diquarks, CC, and anti-diquarks, C bar, or some authors consider genuine CC bar system. This is a complicated calculation. Honestly, we don't know the wave function of tetraquark, especially of the one which was observed, because we even don't know which one it is. So the mechanism of the reaction was almost not studied so far. So our work concentrates on the mechanism of tetraquark production, and I will report the paper by Rafał Maciuła and Wolfgang Schaefer and myself. So this was published beginning of this year. And I will try to address the issue why this fully heavy tetraquark was not observed before LHC, but could be observed at the LHC. And we think it could be even more efficiently produced at FCC. So this is a discovery plot of LHCb. So we really see a peak. Because this is in J-psi system, it is very difficult to imagine that it can be something else than CC bar. So actually, to increase statistics, LHCb combined data for 7, 8, and 13 TV. So this is really a mixture. So this is not really from one energy, but this is a mixture of different energy. Therefore, it is a little bit difficult to analyze from theoretical point of view. This was discussed in this session that the mechanism of quarkonia production is very often not well known. And we have either color singlet approach or color octet approach. And we think also for tetraquark, there could be such two mechanisms, and a priori we don't know which one wins. So we will consider production of 4 quarks, CC bar in color singlet state, but also in color octet state. So here I am showing a mechanism of the production of 4 quarks. This is single parton scattering mechanism. There are several diagrams. This is only schematic picture, and double parton scattering, which is also schematic picture. And we produce in both cases such final states. So actually, some time ago, we worked on 4 quark production in these different collaborations, and these are people who work on this, and we think we understand charm production very well. However, okay, so let me start from single parton scattering mechanism of 4C quark production. We do it in KT factorization. So in this approach, this is a convolution, the cross section for 4 quark production is a convolution of unintegrated gluon distributions, which depend on longitudinal momentum fraction, transverse momentum squared of the partons entering the hard process. They could also depend on factorization scale. And there is also elementary cross section for 2 gluon fusing to 4 quarks. This we know how to calculate because we learned before, some years before. And this elementary cross section is written here in terms of the amplitude here, and this is integration over final state, which is really 4-body final state. In our approach, gluons are off-shell, so virtuality is equal to minus transverse momentum squared of each gluon. We checked, because in principle there could be different mechanism, gluon or QQ bar annihilation. We checked that QQ bar annihilation at the LHC is much smaller, so we can discuss only gluon fusion mechanism. In double parton scattering, one is using double parton distribution functions, which are in approximate way expressed in terms of single parton distribution, single gluon distribution, as it is written in this formula. And usually one is using simplified formula, so-called pocket formula, factorized ansatz, where the cross-section for 4 quark production, this psi represents many kinematical variables. So it's not one variable, but it represents many kinematical variables. And we have cross-section for 1 single parton scattering, cross-section for the second parton scattering. And we have also normalization. And this normalization has some common factor, which is called sigma effective, which for people who do double parton scattering is well known. And there is also combinatorial factor, which depends on identity of the final states. In this case, for CC bar, this is 0.5. So I am sketching the mechanism of tetraquark production. Now I am coming to tetraquark production. So I'm saying first I produce these 4 quarks, and from 4 quarks, I am producing tetraquark and soft gluon. So this is, I will call it coalescence model, but this is very much similar to color evaporation model. So in my calculation, of course, I cannot control space-time distribution of those quarks. All I can do, I can check invariant mass of this four-body system, and I am calculating this cross-section for CC bar production in some window of the invariant mass around the tetraquark. I am taking plus minus 100 JeV to have more or less kinematics, okay. But of course, it cannot give me everything, and I have to have some a little bit arbitrary factor probability of producing tetraquark from CC bar. Of course, this is very complicated issue, and I cannot calculate this probability from first principle, at least in the moment. So let me go to some results. Here I am showing cross-section for 4 CC bar system, and the solid line is for SPS mechanism, and the dotted line, yes, is for double parton scattering effects. So in this case, at 13 TeV, the DPS is by 2 orders of magnitude larger. So one is inclined to say that this DPS dominates also production of tetraquark, which is not completely obvious, honestly saying. So to calculate, so this is 4-quark production. This is very large cross-section for 4-quark production. This is everything in the limits of LHCb, in the acceptance of LHCb. So between 2 and 4.5 in rapidity. And we see that the maximum of the cross-section is very far from 6.9. So we are not really in this range where we have maximal cross-section, but a little bit smaller cross-section at this position of the tetraquark. Here I am showing distribution in transverse momentum of the whole system. And now I am going to the background. Background is production of 2J size. Again, there is SPS mechanism, and there is double parton scattering mechanism. This is the second mechanism. And essentially, we studied both production of 2J size as well as single production of J psi. Of course, due to quantum numbers, as what's discussed in this session, also extra gluon must be emitted. But essentially, we know how to calculate also background. But in the case of background, in contrast to the signal, we can calculate cross-section absolutely normalized. And this is background invariant mass of 2J size. So please look that the background has more or less maximum where the tetraquark is measured. But SPS and DPS have similar size in the case of background. Also, transverse momentum of 2J size. This is in this window around tetraquark. This is a distribution of the background.
Antoni, you have 2 minutes to go.
2 minutes to go, yes. So what are x's which are in these calculations? One x is large because this is asymmetric configuration. Second x is of the order of 10 to minus 5 or even less. So this is for SPS mechanism or for DPS mechanism. What we have done also, we calculated, this is different approach. We calculated fusion of 2 gluons to tetraquark, assuming different quantum numbers of the tetraquark. So this is singlet mechanism, which we consider for pseudoscalar quarkonia, and Wolfgang Schaefer will be talking about this. So we know matrix elements for pseudoscalar and scalar particle production. We also know it for 2+ state, and I will not go into details. In addition, we need form factors because how gluons couple to such system requires also form factors, and the form factors are parameterized by such monopole forms, and lambda is taken by analogy to quarkonia. And this is, maybe this will be a last figure I will show. We are showing PT distribution for scalar tetraquark and for pseudoscalar. From what we learned from the paper of LHCb, this distribution is too steep, so this can be rejected. Pseudoscalar quarkonium, fusion of pseudoscalar quarkonium in this mechanism, gluon to tetraquark fusion, is not good, we think, but scalar is possible. We also checked that 2+ is also possible. Okay, we did the same for FCC, and the cross section is also large, even larger, with the dominance of DPS. And finally, we also did similar calculation for CC bar, BB bar system. So these are such mixed tetraquarks which could exist. But here, the result strongly depends on the mass window. So here we did calculation for 2 mass windows. This is one mass window, and second mass window. And really cross-section strongly depends on this mass window. So we cannot do really strong predictions for this, but we hope that this will be soon measured at the LHC. So this is our hope. So I will finish with conclusions. So we discussed possible SPS and DPS mechanism of tetraquark production. Actually, we are not sure which one dominates. Personally, I think that DPS should be important in this context, because this is 2 orders of magnitude larger cross-section for quark production than SPS. We discussed background. We concluded that FCC could be better than LHC, but this is far future. And also, I think next step would be really to measure 2C, 2B tetraquarks, which cross-section for this is much smaller, but perhaps one can select.
Sorry, Antoni, your time is
I am finishing now. Sorry for being too long. Thank you very much.
Okay, thank you very much. I think we have one question by Nodoka. Please go ahead.
Hello. How much did you use for the sigma effective?
Okay, thank you for this question. We were very standard for this. So sigma effective, we took 15 millibarns. So this is standard for double parton scattering. And also this value, we know that with this value, we can extremely well describe charm production at the LHCb. Also correlation.
Okay.
So this is really value which is checked for charm production. So we believe.
Okay.
So we believe
because actually we analyzed the quarkonium production for the ATLAS and CMS, and for these ones we could find something like 6 millibarn. So for the LHCb, yes, I agree that it's not a very large DPS, but for the ATLAS and CMS, we could find a large DPS for quarkonium involving reactions. We don't know why, but
I have comment to this. I think this small sigma effective for quarkonia is not that the sigma effective is so small, but these are missing mechanisms which are not taken into account in the calculation of single parton scattering. I think we don't control really this 2J psi production from single parton scattering case. And effectively, people take larger value of sigma effective for quarkonia, but I think it's extremely effective. I don't think this is extraction of sigma effective. It is also showing that such sigma effective will describe the data, provided that we know the mechanism of the production.
Okay, all right.
Okay, so let's thank the speaker again. And I think we can continue now with the talk by Paolo. Can you
stop share?
Yeah.
Hello, can you hear me?
Yes,
better now, hopefully.
Yes.
I apologize for the problem. My laptop crashed.
It's fine. I think you Well, okay. You have 10 minutes when you start screen
Okay,
sharing.
yes, I will try to stay in 10 minutes.
Okay, and then
You
you
see
can
the
continue.
slides?
Yes.
Yes, I think I can start from the from
where you
here. I
are.
mean, study of the pentaquark structure in the lambda B gypside proton kaon decay. This probably I went through already. I mean, the evidence was first given by LHCb, and then still LHCb has resolved the two peaks here. The discovery of a third peak on at mass of 4312 with a hint of fourth peak. There was no indication in the GluX experiment. And later on, I mean, now recently, Morion did zero has published on archive. This is not yet a peer review paper, and evidence of 3.1 sigma with an inclusive search in looking to the mass spectrum on J psi proton. So in ATLAS, the study is based on the data of run 1, so about 25 inverse femtobar at 7 and 8 TeV. We have no separation of pi k on proton, which means we have to take all possible combination of light quarks to be combined with the J psi. Light hadrons to be combined with J psi to reconstruct the B hadron. So selection starts with selection of J psi, the association with the two light hadrons, the suppression of the background, which is mostly due to lambda B to J psi lambda star, B to J psi k star, and Bs to J psi phi. Is the suppression is done by putting a cut of the invariant mass of the two light mesons. Finally, there is the subtraction of the combination of the two light hadrons of the same sign. On the right table, you see the definition of the signal region for the lambda B and control region for D0 and Bs together with the combined background shape. Once we select the data, then there is a fit procedure applied to all kinematic distributions. I will not go too much into details here. Essentially, all the invariant mass are fitted. As an example, on the center plot, you see invariant mass distribution of J psi k pi with the peak dominated by the B0 decay to J psi k pi. On the right plot, you see invariant mass distribution of J psi k, actually with the light, one of the light hadrons in the kaon hypothesis. In the bottom plot, which is probably the most interesting, you see the invariant mass distribution of J psi proton kaon decay, where you see all the different contribution from the signal, including the two dashed lines that defines the signal region and the different background. From the fit, we obtain different yields for the lambda B and B0 and the Bs. In particular, we had about more than 1,000 lambda B decaying to J psi proton kaon. Which means we can extract, let's say, the parameters for the in the hypothesis of the two pentaquarks. So this is the fit results that you see here. So a fit procedure is repeated, is applied in the hypothesis of the two pentaquarks with spin parity 3.5 minus and 5.5 plus, which is what has been measured by LHCb. And here you see the results. So essentially, there is a good agreement of this hypothesis with the data, with a probability higher than 50%. And we have about 540 events putting together the two structure. and at that level, the statistical error is at the similar level of the systematic error. The similar fit is repeated in the 4 pentaquark hypothesis, so taking all the 4 structures observed by LHCb. However, we cannot distinguish the 4 structure because of the lower mass resolution and also the limited statistics we had. So we had, in this case, to fix the parameter to the LHCb parameters, while in the case of the 2 pentaquarks, the parameter were left as free in the fit. Also, in this case, there is a good agreement with the data, with the probability higher than 68%. So both 2 and 4 pentaquarks model are consistent with data. The systematics are different contributions. So essentially, there are 4 main contributions to the systematics. The main message here is that with run 1 data, the systematic uncertainties are comparable to the statistical ones, so we can still improve this analysis, adding more statistics, as I said, in run 2, and also we expect to improve the systematics in run 2. Finally, we tested the hypothesis of 0 pentaquark, and here you see the results. Again, I can just go faster on that. Essentially, in the best results, including the extended lambda Vg psi lambda star decay model, we have 1%, somehow something less than 1% probability. So the model without pentaquark is strongly disfavored by the data, but it can be completely excluded yet because the probability is small, but it's not that small. So it's still at the level of 1 per mil or 1% in best case. Currently, ATLAS has the analysis ongoing with the run 2 data with about 5 times more lambda B candidates. So from 1,000, we go to more than 5,000. And with improved mass resolution. So in this channel, we expect a big improvement with the new analysis. Very briefly, another search for tetraquark states. This is the search for the X2BS pi resonance. Actually, the evidence of a resonance was published a few years ago by D0 in the BS pi channel, and was also confirmed a year later in the semi-leptonic channel. However, similar researches performed by LHCb, CDF, CMS, and ATLAS did not show any evidence of the same signal. LHC has enough statistics to be quite precise on this. In the ATLAS case, we have used about 5 inverse femtobar at 70V and 20 at 80V, so run 1 data. I can go directly to the results in this study. So here you see the invariant mass distribution of the BS pi in the 2 different analysis bin with the PT of the BS larger than 10 on the left or larger than 15 GeV on the right. And here where you have the line is the mass corresponding to the observation done by D0. As you can see, there is no evidence of any signal. We have a number of events selected, which is compatible with 0. Since there is no evidence of a signal, we could set an upper limit on the cross section of the X5I68 to BS. So the BS is the reference channel, and actually this ratio is called the rho X, defined in this way. And we can extract the upper limit on rho X using the asymptotic CLS method. The results is summarized here in the box. We have about 1.5 and 1.6% at 95% confidence level as a limit on rho X for PTBS being larger than 10 or 15 GeV.
Sorry, Paolo, you have 1 minute to go.
I am done. As a summary, in this right plot, you see essentially the measurement done by D0 compared with the exclusion limit set by CDF, LHCb, ATLAS, and CMS. And recently there was a combination done by putting together the results from LHC experiment, bringing the limit on rho X below 1%. With that, we have also some analysis ongoing on the ZC, and which is ongoing now with the run to data. The purity is very high. We have about 30 to 40,000 events selected. And actually here we have also an hint of the ZC contribution from the B0 control region of pentaquark analysis with round 1. So here we expect to publish soon the results on ZC. And with this, I go to the summary. So ATLAS has a rich physics program to study exotics heavy hadrons. Here I've presented just pentaquark searches on lambda b to GPSI proton kaon, with the results that both pentaquark, 2 pentaquarks and 4 pentaquarks are compatible with data, and we need more statistics to discriminate. And then all the research on the search for the tetraquark state in the BS pi final state. Search for the ZC state with run to data is ongoing, and results are about to come soon. Thank you very much, and sorry again for the problem earlier.
Thank you, Paolo. Do we have any question? I don't see any. Well, I have one myself. So how is it possible that so what's the difference between the 4 I think it was pentaquark scenario and the 2 pentaquark? Is this just the different angular momentum of the states? Are they supposed to be like partners?
Yes, they are. They have different spin parity. Let's say in the 2 pentaquark states, you have 3 half minus and 5 half plus. In the 4 pentaquark states, they have. Now I don't remember exactly the spin parity value, but they are partners. Let's say.
Okay.
So this is I think was also presented yesterday at the plenary session in the nice talk that was given, looking more, I mean, to the whole LHC results there.
Okay. Thank you very much.
I mean, in our case, we had different, results, because in one case we fix in the 4 pentaquark hypothesis, we fix the parameter to what has been measured by LHCb, and here we just fit our value for the structure. You see better here in the LHCb plot how the 2 are close.
Okay. So if we don't have more questions, let's thank Paolo again.
Thank you very much.
You're welcome. And I think our next speaker is Gary Robertson.
Hi.
Hi.
Can you hear me okay?
Yes.
You can see the slides?
Yes, we can see your slides.
Okay.
So you have, you can start. You have 15 minutes plus 3 for discussion.
Okay, so I'm going to be talking about recent studies of exotic hadrons at the LHCb experiment. So I'm happy to be here giving this talk on behalf of the LHCb collaboration. So in particular, I'm going to discuss 3 recent papers. The first is the observation of new resonances decaying to J-psi-K and J-psi-Phi. The second is the evidence of a J-psi lambda structure and observation of excited chi minus states in the chi b minus to J-psi lambda k decay. and the third is a study of BS0 to J psi pi pi k k decays. So just to motivate why we do these studies, although a lot of this has already been said. So exotic hadrons are ones which have greater than 3 valence quarks. They were first proposed by Gell-Mann himself in his paper in 1964, which introduced the quark model. The first observation of an exotic hadron was the X3872 by Belle in 2003, and this was in the J psi pi pi mass spectrum. So in the lower left here, I've got the plot. This is the J psi pi pi mass spectrum, and you can see a clear peak around the 3872 mass. The first observation of the pentaquark was by LHCb in 2015, and this was recently updated in 2019. This was in the J psi proton mass spectrum. So in this plot here, this is the mass spectrum of the J psi proton. This is the same plot as Paolo just showed. You can see the 3 pentaquarks very clearly. This plot we've again already seen today, so I'm not going to go over it again, other than to say the most recent discovery of these hadrons was 4 new tetraquarks, which were discovered at LHCb, which I'm going to talk about in a moment. So the first paper was the observation of new resonances decaying to J psi k and J psi phi. This mode was already studied. Put 2 links here. And this was done using 3 inverse femtobarns of data, which corresponds to the run-1 dataset for LHCb. So this was a repeat of this mode using the run-1 and run-2 datasets. And in this, we found that we saw 4 new X structures decaying to J psi phi at greater than 5 sigma significance. So I've listed them here. And this is also the plot from the paper. So on the x-axis, this is the mass of the J psi phi. And again, you can see the four clear plots, clear peaks of the X structures. The JPC quantum numbers were also measured as 1++ for X4140 and X4274 at greater than 5 sigma significance, and at 0++ for X4500 and 4700 at greater than 4 sigma significance. We also saw a 3 sigma evidence of a peak around 4 GeV, but this was not significant enough to claim observation, but this could be a possible hint of a ZCS state. And you can see it here on the plot. It's a significant deviation from the data. So this is a new analysis that takes advantage of the full run-1 and run-2 dataset, as I said. This corresponds to 9 inverse femtobarns rather than 3 for the first paper. There's some small changes to the pre-selection. So there's a looser chi-squared IP cut, which is basically the vertex chi-squared value for the kaons, so the fit of that value. And there's also improved machine learning algorithms, which lead to better background subtraction. So the result of this then is we get 6 times more signal yield. So we have 24,000 candidates and 6 times less combinatorial background. And on this plot here, we've got the mass of J psi phi k, and you can see it's a very clear peak. So then we looked at the Dalitz decays. So these are 2 Dalitz plots. On the left, we've got the squared mass of the J psi phi on the x-axis, and on the y-axis, the squared mass of the phi k. And again, I've just highlighted again these 4 X structures you can see very clearly in this decay. In the right plot, we've got the squared mass of the J psi phi on the x-axis, and on the y-axis, the squared mass of the J psi k. Again, vertically, you can see these 4 bands, but there's also some hint of a structure on the horizontal axis, again at about 4 GeV mass, which could be a hint of the ZCS. So after this, a full amplitude analysis was carried out. These are the results here. So we've got the 4 X states from the run-1 analysis in the fit, 2 new X states included in the fit, and 2 ZCS states included in the fit. And so perhaps the best plot to see the 2 new ZCS states is this one on the right, which is the mass of the J psi k spectrum. And then we've also got the J psi phi spectrum and the phi k spectrum. And then we carried out a projection of this fit onto the J psi k mass spectrum. So this plot on the left here on the lower is the well, both plots are the J psi k mass spectrum, but the plot on the left has a slice of J psi phi between 4.25 to 4.35 GeV, and the plot on the right has a slice between 4.35 to 4.45 GeV. And then the blue dashed line shows the fit to the data without including this ZCS contribution. I should say as well, this other ZCS contribution is already included in this fit. So the blue line shows the fit without including this ZCS contribution, and the red line shows it with the ZCS contribution. And you can see that in both cases, it significantly affects the fit, and it's having a good effect on the fit. So just to summarize this paper, the four previously measured X states were found to be consistent with the run-1 analysis. 2 new X states were found, X4630 and X4685, and X4685 was found with a high significance. There were 2 new ZCS states observed in the J psi k mass spectrum, and there was also some measurements made for the quantum numbers, which I'm not going to go through just in the interest of time. So on to the second paper. This was the evidence of J psi lambda structure in the observation of excited chi minus states in the chi b minus J psi lambda k decay. Just to show this plot again, so the motivation for this paper is that, so in 2019, LHCb published this paper with this plot in it, and you can see 3 clear pentaquark signals, and this is a charmed pentaquark. So the idea was that by swapping one of the up quarks in this pentaquark for a strange quark, we can look at strange counterparts. So, for example, in this diagram here on the left, sorry, on the right, no, sorry, on the left, yeah. Well, this is the charmed pentaquark decay. And then what we do is we swap this U quark here for an S quark, and this corresponds then to a strange charmed pentaquark. And this decay has also previously been observed using only the run-1 data set. So there was also motivation to update this to the full data set. So this is the results from the paper. And it's just worth noting as well that this charmed pentaquark with strangeness was predicted to be found in these decays already. So on the plot on the left here, we've got the mass spectrum of the J psi lambda k. And there's 4 different plots here. So the top row is the run-1 data only. The bottom row is the run-2 data only. The left plots are the downstream sample where the lambda decays after the vertex locator. And the right plots are the long sample where the lambda decays inside the veil. And we've also got on this plot on the left, on the right here, the squared mass of the lambda k on the x-axis and the squared mass of the J psi lambda on the y-axis. And again, you can see 2 clear bands here for these chi minus states. So after this, an amplitude analysis was carried out to measure the properties of these states in this decay mode and to look for any contributions from the PCS pentaquark. So these are the results of the amplitude analysis. The plot on the left shows the mass of the lambda k spectrum, and you can see the contributions from the chi 1690 and chi 1820, which are the blue and the green lines respectively, and also a contribution from the pentaquark. On the right plot, we've got the J psi lambda, and again you can see the mass of the significant effect of the pentaquark. So this is the first observation of these 2 chi particles in this chi b decay. And you can see that the contribution from the PCS is 3.1 sigma in significance, so not enough to claim observation, but still having an effect on the fit here. And what was also noted in the paper was that the addition of this PCS state is complementary to the excited chi state. So this plot on the lower left here shows again the mass of the J psi lambda, with a constraint that the mass of the lambda k has to be greater than 2.2 GeV. The dashed red line then shows this fit without the strange pentaquark, and the solid blue line shows the fit with the strange pentaquark. And similarly for the right plot, where on the x-axis we have cos of the decay angle of the pentaquark with another constraint. And you can see in both cases that the addition of this pentaquark helps us fit the data much better. So it's also worth to note that this pentaquark, the mass is close to the threshold of chi C0 D star 0 bar, and because of this, 2 states were predicted in this region. And this is analogous to the pentaquarks, where the first pentaquark state, when re-examined, was split into 2 separate pentaquarks, the charmed pentaquarks, sorry. So a study was also carried out where instead of 1 pentaquark in this region, there was 2. So this is again the same plot as before, but the one difference here is that there's two pentaquark states here. And the masses here were measured to be 4454 MeV and 4467 MeV. But neither of these hypotheses can be confirmed or refuted at this point. So more data is needed. So on to the last paper. This is a study of the BS0 to J psi pi pi KK decays. And the motivation for this one, it gives us a good channel to look for any J psi phi resonances in the BS to J psi pi pi phi decay. So this is what I show on the bottom here, and you see we've got 26,000 candidates. So plenty of statistics. And we can also make measurements of the branching fraction for the BS to X for 872 phi and BS0 to X for 872 KK, where in this case, the KK pair don't come from a phi decay. So these are the results from the paper. On the left plot, on the x-axis, we've got the J psi pi pi mass spectrum, and you can see a clear peak at the X for 872 mass. And on the right plot, we've got the mass of the KK pair. So you can see again in the red here, there's a clear contribution from the BS0 to X for 872 phi. And then this dashed blue line is the BS0 to X for 872 KK, where again, this KK pair do not come from the phi decay. And you can see that they're also having a significant effect. The other thing to note about this plot, the green line represents simulation, and it more or less breaks down at this region. It doesn't describe the data at all. And it was suggested that this could be due to possible F0, F2 contributions and other possible resonances. So then we went on to measure the ratios, free ratios. So this is the ratio of the X for 872 phi to psi 2s phi, the ratio of the J psi with 2 excited kaons to the phi 2s phi, psi 2s phi, sorry.
You have 2 minutes.
Okay. And then the ratio of the K plus K minus pair. So I won't go through this ratio then, but basically, yeah, it's the ratio of which of these modes is preferred to the K. So we also saw a structure in the J psi phi mass spectrum, which is shown here. This was labeled as X4740 and has a significance of 5.3 sigma. But it could also be the X4700 state, which I previously mentioned, but an analysis with more data is needed to determine whether or not this is the case. The BS0 mass was also measured using the psi 2s KK mass distribution, enriched in BS0 to psi 2s phi decays. And this is the most precise single measurement of the BS0 mass to have been performed. This is the result here. So just to summarize, in this paper, these are the results of these free ratios that were performed. This was the first observation of BS0 to J psi with a pair of excited kaons, and BS0 to X for 872 K plus K minus, where the K plus K minus pair don't come from a phi meson. This was the first observation of the X4740 structure. Just to note, one of these ratios in particular was consistent with but not precise, but more precise, sorry, than CMS. And this measured BS0 mass we've combined with other precise measurements by LHCb to produce a new LHCb average for the BS0 mass, which I've listed here. And then just to summarize in total, so I've discussed many new exotic states, in particular 3 new X structures and 2 new ZCS structures. We have evidence of a charmed pentaquark with strangeness, but more work needs to be done to determine this. And we've made measurements of important branching fractions too. But yeah, the story's far from over. So there's more to come from our current data sets in the next few years. And then many more results to come in the future So for example, run 3 and run 4 will collect 50 inverse femtobarns compared to our total of 9 just now. And then with our current upgrade and future upgrades, we'll also improve the detector and be able to fully exploit it and its capabilities. Thank you.
Thank you very much. Do we have any? I see we have one question from Daniel Greenwald. Please go ahead.
On the P sub C pentaquark study that originally came out, there was an attempt to confirm the existence of the pentaquark with a quasi-model independent partial wave analysis that was run, and you could see that there's the phase motion one would expect in the Argand plane. Was any such fit done with the P sub CS?
Yes, so I don't have it anywhere in my slides, but there was a plot into the Argand diagram, and it does perform as expected.
And if I might ask a second quick question, I mean, looking at this Dalitz plane on your slide 15, one could imagine, so around 20 or so, which is where you say this piece of CS is, if you just want to go slightly up, one could imagine having one can see with their eyes, let your eyes play tricks and see another line there. But if you look at your plot on the next slide, you can also see there's a bump at slightly higher mass, etc. And how was the mass? Was the mass left completely free in the fit? Was there an attempt at adding a second state at higher mass rather than splitting this one into 2, etc.?
So I believe the mass was left completely free, yeah. But I'm not sure of the range that it was allowed to float in. So yeah, there is this bump here, but as of yet, not investigated.
Okay, so if I don't see any more questions. So thanks again for the nice talk, and we go to the next speaker, Wolfgang Schaefer.
Yes, hello. You hear me well?
Yes, we can hear you well.
Very good. I can switch.
Can you?
I may share the screen, right?
Yes.
Okay, share.
Okay, we
Very
can.
good. Let's go to a slideshow. Okay.
Okay, you can start.
So thank you very much. As Antoni already announced, I will indeed speak about the ongoing collaboration of us on the production of charmonia in an approach which uses KT factorization and light cone wave functions or light front wave functions for the description of the charmonia's structure. So we will in particular concentrate here on C-even charmonia, and the reason is that within the color singlet approach, which I adopt, the C-even states have a particular simple production mechanism, which is just the fusion of 2 gluons. And those gluons in the KT factorization approach carry transverse momentum and are off-shell. So the production mechanism being simple, you may hope that it can be a good probe of these unintegrated gluon distributions. Just to remind you, the C-even states comprise, for example, the ground state meson eta C, the pseudoscalar, its excited state, and the chi states. Today, I will just concentrate on spinless particles, so on the pseudoscalars and scalars. So the crucial ingredient of any KT factorization approach is the off-shell matrix element. And here we capitalize in our approach on the fact that in the perturbation theory at the lowest order, this 2-gluon fusion in the color singlet to the quarkonium is basically proportional to the same matrix element in the photon-photon fusion. And in the photon-photon fusion, that's an observable of interest by itself, which could be in principle measured in double-tagged E+ E- collisions. So it's common in this type of physics to parameterize the matrix element in terms of invariant form factors. For the pseudoscalar meson, there is one such form factor. And just to give you how this looks in our approach, this form factor can be expressed in terms of some convolution of a hard matrix element with a radial light front wave function of the meson. So in general, your, let's say, master formula looks like this, that the matrix element for photon-photon fusion into the meson is given in terms of some hard matrix elements for the off-shell photons to fuse into a QQ bar state, convoluted with a light front wave function, which corresponds on momentum of the quark, as well as helicity variables. So as I said, for the pseudoscalar particle, it's common to parameterize this amplitude in terms of one invariant form factor. In case of the scalar meson, there are actually two form factors. And you can easily understand they correspond to transverse photons and longitudinal photons. Remember that the photons or gluons are off-shell, so longitudinal polarizations are allowed. Okay, so the light front wave function is the crucial ingredient which parameterizes the structure of the meson. And we will adopt a color singlet approach in which the color singlet QQ bar Fock state basically exhausts the normalization of the wave function. Okay, so you're basically to 100% this meson is a QQ bar state. Now we need this light front wave function, and here we go a slight detour over the going back to the non-relativistic quarkonium wave functions, which come from the solution of a Schrödinger equation in the rest frame of the bound state. Here you see radial wave functions as a function of the relative momentum for a variety of quarkonium potentials, and we use useful parameterizations or tables given by the Prague group. So that's just the wave function in the rest frame, the non-relativistic wave function. What you want to have is the light front wave function, and in order to go to that, you need to perform first a Melosh transform, which maps the spin variables in the non-relativistic approach to the light front spin variables. And you need a way how to go from the momentum, relative momentum in the rest frame to these light front variables, which is given by a mapping given by Terentiev. And then you get light front wave functions depending on Z, the momentum fraction carried by the quark, antiquark carries 1 minus Z, and transverse momentum, relative transverse momentum of the quarks. They look something like that. And those are the radial wave functions which go into our form factor calculations. So indeed, there's a nice cross-check of our approach, namely this transition form factor, this form factor, why it is hidden here, f of q squared and 0 has been measured by the Barbar collaboration. So this is the situation in which only one of the photons is off shell. Okay, the second one is on shell. And in this case, we can check our approach, and you can see that some of the wave functions indeed give a quite reasonable description of this q squared dependence. Actually, the deviation from the data is not so much due to the shape of the wave function, but rather to the quark mass used in the model. So that's a good check on our approach, and we will use these form factors just generalized to two virtualities in our calculations of the hadron production cross sections. So the hadron production now is calculated from the fusion of two off-shell gluons, and we get the cross section by convoluting the unintegrated gluon distributions in the two particles and the two protons with the off-shell matrix element, which is related to the one that we calculate using the standard rules of the KT factorization approach. Well, and some of the gluon momenta, of course, by the momentum conservation make up the transverse momentum of the meson. So in case of the pseudoscalar meson, this is offshore matrix element is indeed just characterized by one form factor, which, as I've said before, for the case when one of the photons or one of the gauge bosons is on shell is actually checked against data. Okay, so we can take our calculation of this form factor into this cross section and evaluate it. There are some interesting points from the, say, theoretical point of view on the KT factorization approach. First of all, if you would look into this formula, what you would realize is that Q1 and Q2, they are essentially proportional to the polarization vectors of these two gluons. And these two gluons in the KT factorization approach are linearly polarized to 100% along their transverse momenta. So this function and integrated gluon distribution F contains information which in TMD approaches in which the matrix element is on shell is contained in two distributions, unpolarized and linearly polarized ones. Okay. And the same approach, offshore matrix element, can also be applied in other observables like in exclusive diffraction, which Isabella Barbiash will present on Thursday. I have shown you the ratio of the form factor divided by its value at the on-shell point, which agrees well with the data. In order to make reasonable predictions of hadronic cross sections, we will normalize the form factor and the on-shell point using standard relations next to leading order relations for the relevant widths. And let's now have a look at some results. First, look into LHCb data. And the LHCb kinematics is, as you all know, the asymmetric case in which we measure in the forward region. And in this case, if you look at the kinematic variables of gluon 1 and gluon 2, you see that these gluons are really strongly separated. One has an x which is bigger than 10 to minus 2, and the other one has very small x, smaller than 10 to minus 4. So that's a very interesting situation which allows us to probe the very small x glue. If you look at projections of these variables, you can see that the large x gluon carries, in fact, small transverse momentum, and the small x gluon carries a much larger transverse momentum. So it's mainly responsible for the kick, for the transverse momentum transfer to the quarkonium. The unintegrated gluon distributions I show here on a plot. They are related to the linear, to the integrated glue, collinear glue by such a relation. What you see here is the unintegrated glue divided by KT squared. Here's just the unintegrated glue. Here you emphasize the small KT behavior, here the large KT tail. And there are basically two types of distributions, ones which have a hard tail and ones which don't. Okay, and they differ very much in the small KT region. This reflects itself also in the results for the PT distribution of the meson. So here we see LHCb data at three different center of mass energies, 7, 8, and 13 TeV. And that's the PT distribution of the eta C, the eta C1s. And you see that basically all gluon distributions which we use, which you have seen on the previous plot, give a quite reasonable or even good description of the data. They would show large differences. The large differences would be reflected at small PT, where unfortunately the measurement is very difficult. Okay, this eta C is measured in the pp bar finite state. This last plot is at 13 TeV. In our paper, there's still a plot with preliminary data, which looked actually worse. So the data have come down a bit. Our description is now a bit better, but there's still some problem at the larger PT. This measured distribution seems to be indeed harder than the one predicted by the KT factorization approach. So there is some room for additional mechanisms, such as the color octet contribution or possibly next to leading order contribution. But remember that in KT factorization, large part of the next to leading order contributions are taken into account. So we also calculated eta C2S. I just flash it. It has cross sections in a similar ballpark. It would be nice to measure it for consistency reasons, but it could be difficult. Here is the integrated cross section in the LHCb kinematic domain. And these are the black points. And you see that for some of our form factors, we get reasonable, quite reasonable description. This has changed here in the preliminary data. This point was higher, and we were having actually quite a bit of a problem. But this integrated cross section comes out now quite reasonable, depending on the form factors you are using, on the wave function model you are using. So here's a very interesting plot. And what this plot shows is the dependence on off-shellness in the off-shell matrix element. Okay, that's the crucial element of the KT factorization, is that the gluons are off-shell and your matrix element depends on the off-shellness of gluons. If you would neglect this off-shellness in the matrix element of gluon fusion, you would obtain such a curve up here. So here the PT distribution comes just from the convolution of two gluon distributions.
Wolfgang, you have 2 minutes more.
Okay, 2 minutes. Thank you. Thank you. I will speed up. But let me just finish this point. So this is what you would do, for example, in a TMD approach. In a TMD approach at the leading order, you would have on-shell matrix element, and that's fine at small PT. At large PT, in the small x kinematics, doesn't seem to work. So you would have to add, in this case, large higher order contributions. So in 2 minutes, I simply flash a bit about the Chi-C. The Chi-C now, as I told you, there are two form factors for transverse and longitudinal photons or gluons, and this reflects itself also in the cross-section formula for the Chi-C. And indeed, here are results which are decomposed into transverse and longitudinal gluon contributions. You see from the total that the total is smaller than TT, so there's also an interference between transverse and longitudinal. And indeed, these longitudinal gluons are something which are not available if you go to a TMD limit. Okay, they are genuine, in this case, higher order contributions. They have some effect due to their interference at large PT. This is, by the way, this is Chi-C0, this is Chi-B0. Okay. So this is just a conceptual point how these factorization approaches differ. And so I may have rushed to the last slide a bit, but I arrive at my conclusion. So we have an approach for KT factorization, which allows us to use photon-photon virtual transition form factors, which can be obtained from light front wave functions of the quarkonium to calculate hadronic production. And this approach, which has only a color singlet component, is quite successful for the eta C. At least at 7 or 8 TeV. At 13 TeV, we could need some additional mechanism, probably at large PT. So the LHC kinematics is very interesting because of its asymmetry, where you probe one very small X gluon distribution. But unfortunately, the gluon saturation effects, for example, which you would like to see, they are not visible at large PT. You have seen that basically all gluon distributions at large PT that we used gave very similar results. So it would be interesting, very interesting, to go to smaller PT, to just the region of the peak of the cross section. Okay, we made predictions for eta C2S. I didn't discuss much the uncertainty due to the wave functions, which are of similar sizes for the unintegrated gluons. And finally, the KT factorization takes into account not only transverse, but also longitudinal polarizations of gluons, which are in other approaches sort of pure next to leading order effects. So thank you very much. I hope I'm still in time.
Thank you very much. Do we have any question? Okay, I don't see any. Okay, I have one myself. I
Yes.
noticed when you compare the different models that you don't take into account a Coulomb potential, like the most simplest model I could think. So
Yes.
is that because it fails?
That's true. That's true. I think they also have a Coulomb potential in the Prague group also provides a Coulomb potential. Yes.
Okay.
It's not particular. You see, the Cornell in principle has a Coulomb tail.
That's right. Yes.
The Cornell has a Coulomb, and you see that it is it has the much. It's not a good plot, but you would see that it has a much longer tail in PT. And in that case, it doesn't give fantastic. It gives a bad description of this form factor. But as I said, that's mainly due to the quark mass. You could argue that in the hard matrix elements, you maybe shouldn't use the quark mass of the potential, right?
Right.
You could argue that you should use a smaller mass than that in the gluon-gluon fusion. Then it would be also better. But yes, that's for the pure Coulomb, we didn't do the calculation. That's correct.
Okay. Thank you. I don't see any more questions, so thank you again.
Thank you very much. I stop to share.
And we move on to the next speaker, Suxian Li.
Hi.
Hi. Can you try screen sharing?
I share my screen PC.
Yes, we can see it. Okay, so Suxian is going to talk about spectroscopy on conventional and non-conventional hadrons at Belle. And okay, so you can start and you have 15 minutes. Please go ahead.
Okay. I'm happy to give a report on behalf of the Belle collaboration. My talk is a spectroscopy on conventional and non-conventional hadrons at Belle. The Belle data has been taken for around 10 years with a total luminosity of 980 inverse fentbar. We have more than 700 inverse fentbar data samples collected and Upsilon 4s, corresponding to around 772 million BB-bar events. For the Belle accelerator, it is a E+ E- asymmetry energy collider with a beam energy of 3.5 GeV for positron and 8 GeV for proton, and its cross angle is 22 megarad. The Belle detector is shown in the right plot like this. And today we will report on several recent results on Belle experiment. The selected topic for conventional hadron as a branching fraction measurement of lambda c to p eta and p pi 0, and the first observation of the radioactive decays of the excited psi ions. We also report the first evidence for X30 at 72 in 2-photon productions. The Siegel-Cabibbo suppressed weak decay of lambda c to p eta and p pi 0 are firstly measured by the BASE3 collaboration. The first evidence for the decay lambda c to p eta with a statistical significance of 4.2 sigma is reported, and they give the branching fraction of lambda c to p eta. No significant lambda c to p pi 0 signal is found, and they set an up limit on its branching fraction and 90% confidence level. The theoretical prediction with the current algebra approach gives the branching fraction of these two decay modes, and the value for lambda C to P eta is in good agreement with the base 3 measurement. And the value for lambda C to P pi 0 is much lower. In this analysis, we try to search for lambda C to P pi 0 signal with the Belle data and improve the measurement accuracy. The basic method for this work is to measure the branching ratio of our signal decays with respect to the normalization mode, and then utilize the knowing branching fraction of the normalized decay to calculate the branching fraction of our signal decays. We take the well-measured lambda C to P pi decay as our normalized modes. According to the formula, the fitted signal events and the detection efficiency are needed. Firstly, we reconstruct the lambda C candidate with 3 charged tracks identified as the proton, cation, and pion, and the vertex fit is performed to suppress the background. After all the event selections, we fit the pKi mass spectrum shown in the left plot and obtain the fitted lambda C signal events. Since there are unknown structure observed in the Dalitz plot from data which is shown in the right plot, we use the weighted Dalitz method to estimate the detection efficiency. And the middle plot shows the Dalitz distribution of the efficiency weighted by data, and we obtain the final efficiency. For our signal decay mode, firstly, we reconstruct the signal decay mode lambda C to P eta. Eta is reconstructed by 2 photons. The momentum of eta in center of mass frame is mainly used to suppress the background. After all the event selection, the invariant mass distribution of P eta is checked in the plot. We find a significant lambda C signal in the spectrum and use a Gaussian signal and polynomial background function to fit the P eta mass spectrum and get the fitted yield of the signal. The detection efficiency is obtained from the signal multicolor simulation. Finally, we calculate the branching ratio and use the branching fraction of the lambda C to P pi to get the measured branching fraction of lambda C to P eta, which is 1.42 times 10 to minus 3. Our result is consistent with the base 3 measurement with improved precision and in good agreement with the theoretical prediction. With a similar method, after all the event selection, we obtain the detection efficiency from the signal multicolor. Then we check the P pi 0 mass distribution, and we find there is no obvious signal excess in mass distribution from data, which is shown in the right plot. Thus, we set an upper limit on branching fraction, which is 8 times 10 to minus 5 and 19% confidence level, which reduces the value to more than half of the current based upper limit and be more closer to the theoretical predictions. The second analysis is about the radioactive decays of the excited Xi-C barons. We know that the Xi-C barons comprise CSU or CSD quark combinations. Many excited states of these barons have been observed and studied. In particular, a recent study reports the measurements of the masses and winds of 2 excited Xi-C states through the strong interaction. These 2 states can also decay via the pi0 decay, but they are harder to see. Also, the higher excited Xi state has been seen in the Xi prime pi mode. So when question appears, what about the radioactive decays to the ground states? In general, the decays of the excited charmed baryon proceed via strong interactions. However, some predictions for the partial winds of the photo transitions indicate that they could be observable. For example, one theoretical prediction shows that the partial wind is over 200 keV for the neutral states decay, which would be seen experimentally, and for the partial wind is less than 10 keV for charged states decay, which would not be seen. In order to study the Xi baryons, we first reconstruct a large sample of ground state Xi0 and Xi plus with good signal to noise ratio. To obtain the large statistics, we use 10 decay modes of the Xi0 and 7 of the Xi plus. The pore mass region, the pore mass distribution for the ground states is shown in the top plot. The upper data point is for Xi0 and the lower is for Xi plus. The 2 sigma winds is selected as the ground state candidate. Then the excited Xi state is reconstructed by ending a photo with the energy requirement. After all the event selections, we fit the Xi gamma mass distribution to extract the signal yield. In this analysis, the well-measured strong decays of 2 excited Xi states are taken as the normalization modes to calculate the branch ratio. The invariant mass distributions for normalization modes are drawn in the bottom plots. The Xi gamma mass distribution are checked with all event selection for the neutral states, which are shown in the upper plot. We can find there is a clear Xi 20 at 15 signal, firstly observed with a statistical significance of 8.6 sigma, and Xi 2719 evidence is firstly seen with a significance of 3.8 sigma. As expected, no signal extents observed in the radioactive decay of the charged states, just like shown in the bottom plot. The branching ratios of the radioactive decays for the neutral states with respect to the normalization decay are given, which is 0.41 and 0.13 respectively. We also give the upper limit on the branching ratios for the charged states at 19% confidence level. This experimental result confirms the above theoretical predictions. The third analysis is about the X3872 production in single tag to photo interactions. The single tag here means the tagging either the electrons or the positrons in the final state. We know the X3872 was first discovered by the Belle collaboration in the decay B2K pi psi, and its spin parity and charge conjugation was determined by the LHCb collaboration to be 1++, but its internal structure is still puzzle. X30 at 72 is not permitted in the decay gamma gamma to X30 at 72. Here, gamma is the real photon. However, it could be produced if one or both photons are highly virtual. Here, gamma star is a virtual photon. This search is performed in E plus E minus to E plus E minus pipette size. Decay process is shown in the picture here. The minus Q squared is the invariant mass Q squared of the virtual photon. The single tag method is used in this analysis, which refers to when final state electron is undetected. By measuring the momentum of the tagging electron, we measure the Q squared dependence of X30 at 72 production. It must have a steeper Q squared dependence than the regular CC bar states. Hence, the signal tag to photon interactions provide information on the structure of X30 at 72.
2 minutes to go, Suxian.
Okay. After the event selection, we show the observed event in the Q squared value versus pipette psi invariant mass with this Belle data. And the psi2s event are weighted, and in the very narrow X30 at 72 signal region, there are 3 signal candidate events observed with 0.11 plus minus 0.10 expected background events. So the signal events determined to be 2.9 with a significance of 3.2 sigma. From this, we obtain an estimated product value of 2 photon decay veins and the breach fraction of X30 at 72 to pipette psi. In the X3915 signal region, there is no signal seen. With future advances in calculating 2 photon decay veins by Belle 2, we expect this method will help to understand the inner structure of X30 at 72. We are still producing exciting results even though the Belle has stopped data taking for around 10 years. Here we report the branch fraction measurement of lambda c, the first observation of radioactive decay of excited Xi ions, and the first evidence for X30 at 72 production in 2 photon interactions. In the future, the Belle 2 will reach the total luminosity of 50 inverse ant bar, which will provide greater sensitivity and more precise measurement in hydrophysics. That's all my talk. Thanks for attention.
Okay, thank you very much. Do we have any question? So, there is one by Wolfgang. Please
Yes, okay.
go ahead.
May I just ask, could you just go one slide back? Did I see on slide 12 you were showing? So I understand you have 3 events of the X, but at fairly large Q squared, right? This was.
Yes.
So this rather suggests that you're producing through the QQ bar state, right? Because did anyone, do you have some expectations, say, what the Q squared dependence would be for such a molecule picture, or you don't know?
The Q squared distribution for the molecule structure will be steeper. Oh no, will be steeper in the lower Q squared value region.
Yes, I understand,
so,
but I wouldn't expect
but there the statistical is pretty lower, and
it's low, yes.
Yes.
But you
it seems flat. It seems flat in the Q squared distribution.
Yes,
but we expected it has a steeper structure in the lower Q squared distribution.
Thank you. Very interesting. Thank you very much.
You're welcome.
Okay, so I don't think any more questions, so let's thank Suxian for his very interesting talk. And let's move on to the next speaker. So it's Kazuhiro Watanabe. Hi. Can you try screen sharing?
Yep. So can you see?
Okay, we can see your slides. Okay, so next speaker is Kazuhiro Watanabe on QCD evolution of twist 2 and twist 4 fragmentation function for heavy quarkonium production. And okay, you have 15 minutes. Okay, so please go ahead.
Thanks, Miguel. So yeah, first of all, thanks for all the organizers who make it possible to set up this workshop, and thanks everybody to be here. So today I'm going to talk about the QCD evolution of twist 2, twist 4 fragmentation function for heavy quarkonium production. So this talk is based on the work with Kali, John Chu, and Joe Stam. So we are preparing this work. So we are finishing up this work. So okay. So first of all, quarkonium production mechanism has been interesting challenge to QCD since over 40 years. So since the website was discovered, so nowadays NRQCD factorization has been successful in describing quarkonium production in hadronic collisions and high PG. So several groups have made comparison between NRQCD at next to leading order level and with data. So these four figures are showing the PG spectrum on the website as a function PG, and so different group gave a very nice agreement. So they extracted a long distance matrix element. Then here's the issue. So long distance matrix element in NRQCD factorization should be inverse. However, so difference says the number are not the same, and even the signs are different for each set of long distance matrix element. So much more work is needed to clarify quarkonium production mechanism at IPT. And this is an underlying motivation of our work. So let's think about the high PT quarkonium production. So at high PT, we can separate short distance part and the long distance parts. And for short distance part, we can compute calculate the short distance part perturbatively. Meanwhile, for long distance parts, the theoretical treatment is not so clear. So nowadays, we have been so far we have been using some models or NRQCD factorization approach. At leading order, so in alpha S expansion, so the cross sections gives 1 over PT to the 8th powers. So this, for example, this diagrams give out this PT. So 1 over PT to the 8th. However, higher order correction give more lead to harder PT spectra. Then of particular importance is the higher order corrections also bring large logarithmic corrections. So these guys should be enhanced even if the alpha S is small. So that we must be careful about the diagram in double expansion. So alpha expansion as well as velocity expansion. So to clarify the importance of the higher order correction and especially large log corrections, which we will study high PT quarkonium production in QCD factorization framework with the fragmentation functions. And in QCD factorization approach, the cross section so we first expand the cross section in 1/pt first. Then for each contribution, we expand the perturbative factorizable short distance coefficient in alpha s. So the cross section in the quarkonia production cross section up to next to leading power expansion can be written like this. So this short distance coefficient P and this next to leading power short distance coefficient. And these guys include the collinear pattern distribution function who each being hadron A and B or P and P. Yeah, in PP collisions, so this guy is a P and this guy is also P. So there are two fragmentation function here and four fragmentation function that here. So then the large log correction. So we can take large logarithm corrections into the fragmentation function at twist 2 and twist 4. So then we can write down some matching conditions. So the cross section, the quarkonia production cross section, in general has some cross section in the QCD factorization with fragmentation function, including QCD evolution equations, and also this guy is cross section in the QCD factorization with the fragmentation function expanded to the fixed order in alpha s and velocity. So then at lower PT, the NRQCD, fixed order NRQCD factorization should take over the QCD factorization framework. So, and also at moderate PT or low PT, this guy this time remove the double counting contributions from these two results. So using this QCD factorization frameworks, so let's think about, we should consider hadronic quarkonia production. So very interestingly, so the QCD evolution, so twist 2 from single pattern fragmentation function and twist 4 double pattern fragmentation function that coupled through the quantum evolution. The scalar evolution on twist 2 fragmentation function obeys the usual D graph evolution plus this nonlinear mixing term. Then for twist 4 fragmentation functions, so these guys obey the D graph like linear evolution equations. So we must solve these evolution equations simultaneously. So about input fragmentation functions. So the input fragmentation functions have been derived using the QCD and NRQCD projection operators in final state, then the fragmentation function involves the long distance matrix element here. So before looking into the quantum evolution effect of the fragmentation function, let me make some remarks on the some preliminaries. So first one is the fixed order calculations in NRQCD factorization. So as I said at the beginning of this talk, so nowadays the NRQCD factorization, NRQCD calculation at next to leading order level can describe the PT spectrum quarkonia and also its there's a polarization. So in hadronic collisions. However, so we must be you have to keep in mind that in the NRQCD factorization at next to leading order, so some transverse components of short distance coefficients could be for P wave QQ pair production can be negative. So of course, it's depends on the scheme dependence. It has a scheme dependence, but so the transverse component of short distance coefficients could be negative. So we could have some cancellation between the S-wave contribution, the S-wave production, and the P-wave production. So we should be careful about this point. Yeah, another point is that QCD factorization and leading order with input fragmentation function can reproduce the complicated NRQCD next to leading order result at high PT. So the comparison by channel show that the PQCD, so QCD factorization result at leading order coincide with an NRQCD at next to leading order at high PT. So there are still a couple of steps towards solving the evolution equations. The issues are for 3-4 fragmentation functions. So these guys in principle have several integral variables. So it makes numerical calculations so complicated. So that's why we should think about one simplified situation since the producer heavy core pair is dominated by its initial state. So we may expand the short distance coefficient and also the evolution columns on lower budgeted side at each evolution step. So yeah, around you set that relative momentum. Yeah, we can take a relative momentum 1/2. So then we can simplify the cross section at next to leading power like this. So this guy now depends on the new 2:4 fragmentation function, and yeah, we can simplify the evolution equations for 2:2 and 2:4 fragmentation function. So now we can solve this evolution equation in moment space numerically. So it's very easy for now. So, and then we can convert the numerical solution of these evolution equation into the ones in position space using inverse main transformation. So about input fragmentation function, we can take the perturbative calculated short distance coefficients. However, as z goes to 1, so NRQCD factorization is not so reliable. So because the short distance coefficient include the delta function term and the log 1 minus z term and plus distribution function terms. Then to mitigate, to deal with these terms. So for example, for delta function term, we mimic the delta function terms using this setup. So then using this replacement, so we can have we can confirm the transition probability. For example, say from gluon to quarkonium transition probability should vanish at equal 1. So then, this is more makes sense physically. So about log 1 minus zeta, log 1 minus z type divergence, we can mitigate this term, including some separation factor. So endpoint resummation should account for this separation factor and also plus distribution function. So we just about this terms, we just take first moments of plus distribution function and then add them into the input fragmentation function. Okay, so I'm showing the
2 minutes to go. Fine.
Okay, thanks. The scale evolution of single pattern fragmentation function. So there are 4 leading channels. So from single pattern to QQ bar, 3s1 singlet, 3s1 octet, 1s0 octet, and CPJ octet. So for each plot, I'm showing the numerical result at mean square 25 GeV square and 10 to the 4th GeV square. So the important point is that the QCD evolution the scale evolution of fragmentation, the quantum evolution change the shape of single particle fragmentation function so much. So, and also the nonlinear, so we can obtain the nonlinear evolution effects, but it's actually the nonlinear evolution effects are more profound in 1s0 octet channel and 3s1 singlet channels. So this is the same plot for double pattern fragmentation function at this4. And again, so for each channels, I'm showing the numerical result at 2 different scales. So, okay, so we test the single pattern production cross section on leading power, using leading power expressions. So this single pattern production cross section of the function PT at the LHC energy. So we have already confirmed that convoluting the pion fragmentation function with this leading power cross section reproduce the data on pi plus production yield in proton-proton collision at leak energy, the leak energy. So we can confirm. We have confirmed our numerical results with good job. So this is that here. So we are comparing the next to leading power corrections to the leading power corrections. So at the same energies. So what you see here is that leading power contribution is very important at large PT. Then next to leading power contribution steeply falling, but so both contributions are comparable at lower PT. So we converted the fragmentation function at T3 and T4. So this is leading power contributions with fragmentation function. Without long distance matrix limit, and this is the next to leading power contribution. So now, I put equal weights. So we just set the same weights for different long distance matrix elements. So from this plot, we can see that so produce a single pattern is likely to become. Thanks.
If you could wrap up.
Okay, likely to become 3s1 octet. Then double pattern is a Q-cube pair. So Cook pair is likely to become a 1s0 signals. In this insert, you can see that we compare the color octet channels to we can take a ratio. So we color octet channels to color singlet channels. So eventually we have to sum the leading 4 channels with relative weights. So to our knowledge, so we can take some set of long distance matrix elements. For example, if we use this sets, so the leading power contributions does a good job. So we can reproduce the order of magnitude and the trend of PT spectrum. And the next 2 leading power corrections are suppressed by 1/PTs, but it's at lower PT, so this next 2 leading power contributions are very important. So before closing my talk, so we can try to use the following set of long distance matrix elements. So eventually we have to perform a global data analysis to extract to fit the long distance matrix elements. But for now, so we can try some test sets of long distance matrix elements tuning by hand. For example, choice 1 is more or less realistic choices, but the sets choice 2, 3, 4 are extreme choices. So by data comparison, so given smaller values of long distance matrix size for 3s 1 octet and CP 0 octet channels, so the QCD factorization approach with fragmentation functions describe the data about the PT spectrum. Also the polarization of J psi, because the one now for example, so using these channels, using this set, so the 1s0 octet channel is the dominant source. So here is a summary. So now we are starting to refit the long distance matrix elements using QCD factorization formula with yes, twist2 and twist4 fragmentation function. Thank you.
Okay, thank you very much. Do we have any question? So I see one. Okay, Charlotte, please go ahead.
Hello, thank you for your talk. I liked it. I was wondering if you can expand this formalism also for exclusive production, and if so, if the exclusive production would help you to constrain your fragmentation.
Yeah, possible. Yeah, thanks for your comments and questions. I'm not sure. So because so now we are thinking inclusive production, inclusive processes. So yeah, of course we have to be careful about the definition of fragmentation function in exclusive process, but yeah, I'm not sure. I'm not so sure, but as far as we consider high PT quarkonium production, yeah, we can apply the similar procedure, similar method to say other processes. Yeah.
Okay, thank you. Of course, high PT exclusive will be hard.
Yeah. So well. Of course, yeah, as I mentioned, at lower or moderate PT, we have to switch from the QCD factorization framework with fragmentation function to fixed order NRQCD calculations. So yeah, I don't know. So yeah, interesting questions. Yeah, so we will think about that.
Okay.
Thanks. Yeah.
Thank you.
Okay, so I see no more questions. So let's send Kazuhiro and all the speakers.
Thank you.
Of this session. And okay, so and the session is over. Yeah. I guess that's it. Okay, thank you very much.
Thank you for coming, everyone. See you tomorrow.
See you.
Bye.